Now, this is going to be Mrs. Kubisek's video, but I did want to say, you guys, since this is the last video of the year, this has been craziness doing this flipped curriculum. I'm glad you were here with me for the ride on this. You guys worked so hard. Honestly, the best scores I've seen out of all the years of teaching this class. You guys are amazing, and enjoy the last video by Mrs. Kubisek. We'll see you guys in class.
All right, thanks, Ms. Fliniak. Here we go. So let's go ahead and get this party started. We're going to talk about dilations in this very last section. And if you remember, in our first semester, we talked about dilations as transformations that actually change the size of a figure, but not its shape. So when you're talking about a dilation, when you're going from an image to a pre-image, the figure under a dilation is similar to each other, but they're not going to be congruent because they are not the same size. So for example, I've got the pentagon here and the red pentagon here. They are definitely the same shape, but they are not congruent because they are not the same size. Now, for example, why don't you go ahead and take a minute here to figure out whether A and B are actually considered dilations. So if you think about it, take a look at A and B and figure out if they're dilations. Now, if I look at A, I'm thinking to myself, well, you know what? I've got the blue one here and the red one here. Do they look to be the same exact shape? Absolutely not. So this is not a dilation from one to the other. But if I look at B, yeah, we would say this is indeed a dilation because from the red to the blue, they maintain the same exact shape. However, they are definitely not the same size. So this one would be, yes, you have a dilation. So now let's go ahead and take a look at the dilations themselves. If I have a dilation, which we would consider a similarity transformation, it is just a transformation in which the lines connecting every point P with its image P prime, they're all going to intersect at this point C, and that point is called our center of dilation. And when you really look at the ratio that occurs, the distance from C to P prime compared to the distance from C to P, that's going to be the same for every single point P that we're going to utilize. Now, we've talked about scale factor before, and we're going to use the letter K to represent our scale factor. It's just going to be, well, when you talk about scale factor of any dilation, it's the ratio of the linear measurement of the image to a corresponding measurement of the pre-image. So if we're looking at this one in this figure, if I compare my P prime, Q prime, the length of that, to PQ, the length of that segment, that's going to be my scale factor. So our scale factor here would be P prime, Q prime divided by PQ. Now we know that dilations can either enlarge a figure or reduce the dimensions of the figure proportionally. And a dilation with a scale factor greater than 1 is called an enlargement. Okay, so we could expand, we call it an expansion also. It's taking the original figure and making it larger. So for example, if I took 129% of the original figure, or if I had a scale factor of 2.5, or if we would say, oh, it's 3 times as large as the original. That would be our enlargement. Any dilation that occurs with a scale factor that's greater than 0 but actually less than 1 is called a reduction or a contraction because it's actually getting smaller. So you're looking for percentages that would be smaller than 100% but greater than 0. So for example, 75%. You're looking for values that would be decimals in the case that they would sit between 0 and 1, like 0.5 or 0.6 or 0.7825, or you would have it where we would state that it would be 1/4 the size, or 1/3 of the size, or half of the size. Now, if a scale factor of a dilation is negative, then we're going to say that the pre-image is actually just rotated by 180 degrees. So that's really important that you might want to take a look at. All right, so for example here, what we're going to do is we're going to draw the image of not a triangle, sorry about that, it's a rectangle, WXYZ under a dilation of a scale factor of 2. So really we're enlarging this. So what I've got here is I've got my center of dilation, and I've got my rectangle WXYZ. And what we're going to do is we're going to go ahead and we're going to draw those lines in that connect from my center of dilation through the vertex of the figure. I'm going to do 2 of the vertices at a time here. I'm going to pick X and Z to throw those lines through. And by doing that, what happens is it allows us to say, okay, whatever the distance from X to Z was, let's say it's 1 centimeter here, if I measure it out, which you should, you're going to double that measurement. So that measurement now, by a scale factor of 2, would actually be 2 centimeters for my new image. Now, it means the distance from X prime to Z prime would be 2 centimeters. So I'm going to put it right here, X prime and Z prime, because of course I measured it out and I went as far as I had to until I got this distance to be 2 centimeters. The next thing you're going to do is you're going to go ahead and we're going to draw in the lines that connect my center of dilation from P to Y and from P to W. It's getting bad, guys, I know. Hang in there with me. So then I'm looking for the same thing wherever I can get it through a distance of 2 if this was 1 centimeter, because I'm doubling it. Oof. Imagine it was like this so that I could get a rectangle in here. So I get W prime and I have Y prime down here. All it's doing is getting you to utilize that center of dilation and the lines that go through the vertices to assist you in drawing your image. I know it looks horrible, but hopefully yours looks a little bit better on your page, okay? Can you do me a favor? Can you try out the next example? Same concept. You're going to have Q as your center of dilation, but this time you're going to have a scale factor of 3 that goes from your original triangle, look at me, I'm saying triangle now, jeez. Your rectangle RSTU, and then you're going to draw out your rectangle R prime, S prime, T prime, and U prime. So go ahead and try that out now, and when you're all set and ready, hopefully I'll have something drawn that looks like a rectangle for you guys when you start the video up again. Alright, promise not to laugh, but this definitely is not the best diagram that I've ever drawn, but it gets the point across. So what we've done is we've taken that scale factor 3, and now I've got R prime, S prime, T prime, and U prime according to the lines that went through the vertices from our center of dilation, and it looks like I took this and I dilated it by a scale factor 3. Don't measure mine because it's not exactly on 100%, but I'm going to suggest that when you're doing these problems, you use a ruler and a straight edge. Yours are going to look so much better than mine if you do that, please. So how can we utilize dilations in somewhat of an algebraic sense? In our example here, we've got a sketch of a flower, and we're saying that 4 inches on the sketch represent 1 inch on the actual flower itself. And if a flower has a 3-inch diameter in the sketch, we want to find out what would the diameter of the actual flower be. So we're just using that scale factor kind of thing. So when you normally set these up, your best option is to take whatever the sketch distance is and divide it by the corresponding actual distance, and then set that equal to the other sketch distance, the diameter in this case, divided by the actual diameter. Now we know that let's say the length, okay? Let's say the length of the flower is 4 inches on the sketch and 1 inch actually. We're going to take 4 inches divided by 1 inches, and we're going to set that equal to our 3-inch diameter on the sketch over x, because that's what I'm trying to solve for. So this is really our fraction, 4 over 1, 3 over x, and we're going to solve. When you solve this, because you're doing an equal sign between 2 fractions here, you're going to do your cross multiplication. Our cross multiplication means we're going to have 4x equals 3 times 1, which is 3. And if I divide by 4, I get x equals 3/4, otherwise known as 0.75 inches. So the diameter of our actual flower, the actual diameter of our flower is going to be 3/4 of an inch, or 0.75 inches. Now, anytime you want to talk about dilations in the actual coordinate plane where I give you points, not too hard to do. If I tell you that P is in the pre-image of our figure, and we're going to take that and we're going to use a dilation centered at the origin, and the scale factor is going to be K, then the image point, P prime, is going to end up being Kx, Ky. All you're doing is taking that scale factor and you're multiplying both your x and your y coordinates. I know I've stated this before, but we're going to state it again. If the scale factor of a dilation is negative, that means the pre-image is going to be rotated 180 degrees. Also, if k is greater than 0, we say that dilation with a scale factor of negative k is going to actually be equivalent to the composition. Remember, we put 2 things together. It's a composition. It's going to be a composition of a dilation with a scale factor of k that is rotated 180 degrees about the center of dilation. So if I ever am working with a scale factor that's a -1, what you're going to do is you're going to do the regular dilation with a scale factor of k. So here's my pre-image. I'm going to do the regular dilation of a scale factor of k, and then we're going to rotate it 180 degrees. So it's a composition of two transformations. So for this example, what I'd like for you to do is I want you to draw the image of the triangle with the vertices of P, Q, and R. And what we're going to do is we're going to take that under a dilation of a scale factor of, if you don't have it written, it's a -1/2 that we're going to do. And we're going to do this centered at the origin. So if we're going to do a scale factor of -1/2, remember, that's two things you're going to have to do to this. Not only are you going to have to multiply every single coordinate that we have here, the x's and the y's, by a half, you're also then going to take this and rotate it 180 degrees using the transformation that you've done before with 180 degrees about the origin. So I'd like for you to do a couple things. I want 3 columns here. I want your P, your Q, and your R originally. Then what I want you to do is I want you to tell me what the coordinates for the new P prime, Q prime, and R prime would be after you've taken and done a scale factor of 1/2. Okay, so you're going to do your K of 1/2. And you're going to tell me what the new coordinates are for these. After you're done with that, you're then going to take those new coordinates and you're going to rotate them 180 degrees to give me the final one. So why don't you go ahead, take some time now to do that, and hopefully when you start the video up again, we'll have the same diagrams drawn. All right, so this is what we have. We have our new image that we're working with. The points that I ended up getting for P, for the P double prime, were 2, -2 after a 180 degree rotation. Remember, when you rotate 180 degrees, you take your coordinates and you negate the x and the y. That's why it's 2, -2. After we took our q's, which we multiplied by half each one to get the -1, -1, so I got q prime was -1, -1, and then I rotated 180 degrees, so I got q double prime was 1, 1, and lastly, r by multiplying by half, scale factor of half, we got r prime to be 2, 0, and then r double prime by a rotation was -2, 0. So we've got all of that plotted out. So our PQR, our original triangle here, we did a scale factor of a half, so it shrunk down, and we did a rotation of 180 degrees. So this is what our image now looks like. That is it. You are done. That is the final video for this class. It has been an absolute pleasure. Make sure, and don't forget, that if you have any questions whatsoever, that you ask us in class, and it has been a pleasure. We will see you tomorrow, guys.